Hybrid search gets scary in SaaS when one tenant can leak into another. I'll build a Postgres setup with row-level security, pgvector, and full-text search to prevent that in Python. This is the workflow you'll know how to run when we're done, which indexes tenant-tagged documents and performs a tenant-isolated hybrid search that prevents cross-tenant leakage. I'm Professor Pi, teaching search and IR with simple Python. Multi-tenant search is an operational problem. You want one database that serves many customers without letting one see another's data. That means safe access, predictable performance, and search quality that mixes keyword matching and embedding similarity. Postgres gives us practical tools for this because it can enforce isolation at the database layer and also host both semantic and lexical indexes. The big win is simple. Row-level security stops accidental leaks by making the database itself refuse to show other tenants' rows. Full-text search gives fast keyword hits. pgvector lets us store embeddings for semantic similarity. Together you get a single, auditable system that supports hybrid queries without moving documents out to a separate vector service. We will build a small demo that shows this working end-to-end. I will set a session tenant, create tenant-tagged documents, add a text index, add embeddings, and then run a hybrid rank that mixes term relevance and vector distance. Nothing exotic, just clear steps so the code maps to what you will do in production. Next, we set the session-level tenant in Postgres. This snippet connects to Postgres using psycopg and sets a session variable that carries the active tenant. The call psycopg connect opens one connection, and con autocommit ensures each command applies immediately without an explicit commit. Inside the context manager, the cursor executes a set on app.tenant, so later queries can read the value securely within the same session. The function currentSetting reads the gook back, which we store in the variable t to confirm the value being used. Keeping tenant in a server-side setting avoids trusting the app layer to add filters on every query. The printed tenant proves the session now carries the isolation hint for RLS policies. Now we create the table and enable policies. This example creates a simple docs table and applies row-level security using psycopg and Postgres policies. The table has a tenant ID and a short title, with a unique constraint to keep inserts idempotent during reruns. 2 rows are inserted for tenants T1 and T2. Then RLS is enabled, so policies can restrict reads. The policy docs tenant uses currentSetting on app.tenant, ensuring queries only see rows matching that tenant in the active session. Finally, the query count reads through RLS, so with app.tenant set to T1, the variable n reflects only that tenant's rows. The printed count shows tenant isolation is already working at the database layer. Next, we add text content and a full text index. This code adds a body column, materializes a tsvector, and runs a Postgres full-text query using psycopg. The update fills tenant bodies so the text has meaningful tokens. The generated column tsv stores English normalized terms from title and body. And the gen index speeds matching for tsv at to ts query. With RLS already active, the select returns only rows for the session tenant, making text search inherently tenant-safe. The variable title captures the best match for the simple term setup under the current tenant. Increasing text richness can improve recall, while indexing keeps latency low as data grows. The printed title confirms full text retrieval works without bypassing RLS. Now we add vectors and run a nearest neighbor lookup. This snippet enables the pgvector extension, adds an embedding column, and performs a nearest neighbor search using psycopg. The emb column stores fixed length vectors, and we update both tenants with contrasting embeddings. The query uses the X operator for Euclidean distance and orders by D to find the closest match to QV. Because RLS is already in force, the search only considers vectors from the active tenant, keeping similarity lookups isolated. The variable D holds a real value distance, so you can tune how tight a match you need. Making QV closer or farther from the tenant's embedding will decrease or increase D accordingly. The printed distance shows the vector hit quality for the current tenant. Next, we combine both signals into one hybrid score. This example combines Postgres full-text ranking with pgvector distance in one query using psycopg. The variable Q holds the text query, and QV is the embedding for semantic intent. The expression 0.7 times term significance rank highlights term relevance, while subtracting 0.3 times the vector distance rewards semantic closeness. RLS still wraps the query, so only documents belonging to the session tenant can participate in ranking. We can tune the weights. Increasing the text weight prefers exact keyword matches, while increasing the vector weight promotes semantically close candidates, even if keywords are weaker. The result title and composite score reveal the top tenant-safe hit under a practical hybrid strategy. This toy demo maps directly to a real product flow. In production, you will set the session tenant as part of each request. Populate title and body from your ingestion pipeline. Materialize tsvector updates. Compute embeddings with your model, and then run the hybrid query with weights tuned to your users. All of that stays inside Postgres, so auditing and backups are straightforward. Recap: it is a hybrid tenant-safe search using RLS, full text, and pgvector. Use it when you need single database multi-tenant search with auditable isolation and mixed lexical and semantic relevance. Caveat: design RLS and session handling carefully, because a misset session variable still defeats isolation. Next step: tune the hybrid weight between text and vector in the composite score to match user expectations. Then measure retrieval quality and latency as you adjust it. If short, practical IR helps, subscribe and watch the IR videos.